In this lesson, we're going to look at Newton's first law and how we begin to use that to solve problems dealing with equilibrium. So we talk about equilibrium. These are objects that are in a constant state of motion, and they will remain in a constant state of motion unless they get acted on by some net external force. There are three key points to remember when dealing with equilibrium problems. The first one is that there are two different situations where Newton's first law applies. The first one is that if an object is at rest, it stays at rest. The second one is that an object could be moving at a constant velocity, because constant velocity is a constant state of motion. Same speed, same direction. The second point to remember is that external forces can still be acting on the object as long as they act in a way they cancel each other out. So if you can add up all the external forces and get 0 as your sum, this applies. The third key point is that vector addition is very handy for these types of situations. Because forces are vectors, we need to include that information when we develop our solution. So let's look at an example problem, look at how we begin to work through a problem involving equilibrium. So here we have a stoplight that has a mass of 50 kilograms and it's hanging from a cable. And we want to determine what is the tension in the cable. So my first step in any one of these is to draw a free body diagram. Identify what forces act on the object and what direction those forces act on the object. So for the stoplight, we obviously have two forces. One is weight or gravity, which I could calculate by doing 50 kilograms and multiplying by 9.8, the acceleration of gravity. And the second one is the tension in the cable. It's worth pointing out there are no other forces that are acting on the cable or on the stoplight in this situation. The second one is to apply Newton's first law. So to say the sum of all forces must equal 0. And I know the sum of all forces equals 0 because the stoplight is just hanging here. It's not moving. And so what that means is if I take the tension and subtract the weight, I should get 0. Now, why did I make the weight negative? Well, in this case, I know these two forces are acting in opposite directions. I just choose one of these directions to be the positive direction. I think in this case it makes sense to make up the positive direction, which makes down the negative direction. So if you're going to add these two vectors together, it'd be tension minus weight. And so I could also substitute in what I know weight is, mass times gravity, mg equals 0. So there's my statement for Newton's first law, T minus mg equals 0, and that really helps me guide where my solution is. My third step is algebra. Solve for the unknown. In this case, tension in the cable is the unknown. So if I know T minus mg equals 0, I could add mg to both sides and get T is equal to mg. From here, I could do some math. Plug in what I know and calculate. And so I can plug in the mass of the object, 50 kilograms. I know the acceleration of gravity g is 9.8 meters per second squared. And if I take 50 times 9.8, I get 490. Now it's worth pointing out here we have a new unit. The unit for force is a Newton. And so a Newton is really a kilogram times a meter per second squared, if you want to think of it in terms of its base units. Of course, Newtons come from Isaac Newton, same guy for Newton's laws. So he is the unit of force named after him, as well as laws responsible for forces. One of the things I generally say about physics, or really science in general, is that if you get a law or an equation or a rule named after you, that's a big deal. If you get a unit named after you, that's a big deal. If you have both an equation or a rule or a law named after you and a unit named after you, you're a really big deal in that case. So in this case, Newton is a really big deal. Now my second question is kind of a modification of the first question. What if instead of having one cable, I had two vertical cables? What is the tension in each of the cables? So if I have my free body diagram, I now have two different tensions acting upward. Well, where's my second tension? There it is. Sorry. So I have two different tensions acting upward, T1 and T2. And so when I apply Newton's first law, I'm going to say sum of forces equals 0. So T1 plus T2, those two forces acting in the same direction, minus W equals 0. And what I'm going to say about T1 and T2 is I'm going to say they're probably equal to one another. And the reason why I'm going to say they're probably equal to one another is there's nothing to suggest that one of these is bigger than the other one. In fact, if we think about something being supported by two cables, it'd be logical to assume if those two cables are vertical that they both have the same tension or force acting on them. I will caution you in that just because an object is being supported by two cables does not always mean that the tension in those two cables are the same. This is kind of a special case related to two vertical cables that each one is supporting half the weight. And so I could say 2T, whatever the tension in each cable is, minus mg equals 0. So from here I can do my algebra. Add mg to both sides, divide both sides by 2, so the tension in each cable is mg divided by 2. And I can do my math, plug it in and calculate. 50 times 9.8 divided by 2 is 245 newtons. There is the tension in each cable. It's worth pointing out the tension in each cable is half the tension in a single cable. We could keep moving this forward and we could say, what if we had 3 cables? Well, it's probably a third of the weight of the stoplight is 3 vertical cables. So the more vertical cables, the less tension each one has to support in this case. So I have another example problem. Let's consider the same stoplight supported by 2 cables, but let's say that the cables are not vertical as shown to the left. Are the tensions the same in the cables? Well, not necessarily. If not, which of these two is larger? Is it the one that is more vertical or the one that's more horizontal? Oh, I don't know off the top of my head. The next one, do the tensions add up to the weight of the stoplight? I don't know, do they? That may not necessarily be true in this case. So what we're going to do in our next lesson is we're going to start to look at a problem like this. How do we begin to deal with a situation where it's not as simple as all the forces add up to be 0? How do I deal with forces acting, in this case, in multiple directions, both horizontally and vertically?